This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, the topic is problems on principal stresses and strains in mechanics of solids. Here, the problem on stresses on oblique section of a body subjected to a direct stress in one plane. The problem is a wooden bar is subjected to a tensile stress of 5 megapascal. What will be the values of normal and shear stresses across the section, which makes an angle of 25 degrees with the direction of tensile stress. So, according to the problems, the data is showing on a figure. Here, sigma is given, it is the direct stress. Direct stress is nothing but the stress which is acting perpendicular to the plane, which is equal to 5 megapascal. Both are equal in magnitude in opposite directions. And AB is representing the oblique plane, which is making an angle of theta measured in clockwise directions. According to the problems, it is equal to 25 degrees now. That is theta is equal to. Now, we have to determine the an oblique plane, that is the AB, shear, normal and resultant. So the given data in the problem is tensile stress is equal to sigma is equal to 5 megapascal, already shown in figure now. The angle made by the section with the direction of tensile force or tensile stress, or in other words along the x-axis, it is represented theta, which is equal to 25 degrees now. The normal stresses across the section is equal to normal. Across the section, here it is nothing but equal to normal is nothing but like this, and it is normal, and shear is nothing but acting like this. Here it is the resultant now. These forces we have to determine now. Normal means this force is equal to normal stress across the section is equal to sigma n. According to the previous derivations we got sigma by 2 minus of sigma by 2 into cos 2 theta now. So, sigma is equal to 5 megapascal. Here 2.5 sigma by 2. Here sigma by 2 into 2.5. Cos 2 theta is equal to cos 2 into 25. It is equal to 50 degrees. From this relationship we got 2.5 minus of 2.5 into cos 50 is equal to 0.6428 megapascal, or in other words it is equal to 2.5 minus 1.607, it is equal to 0.89 megapascal. Similarly, the shear stress across the section is equal to tau is equal to sigma by 2 into sin 2 theta. Here sigma by 2 is equal to 2.5, sin 2 theta is equal to sin 50 megapascal, which is equal to 2.5 into sin 50 is equal to 0.766. It is given. It is equal to 1.915 megapascal. The second problem is it is related to subjected to direct stresses in two mutual perpendicular directions. That is here now the object is there which is having uniform cross section area, having thickness is equal to 1 unity. It is subjected to two direct stresses. One is along the x direction, it is represented as sigma x, and along the y direction sigma y. Both are intensile in nature. That is, according to the problem, they are treated as the positive stresses now. So the given data in the problem is here now. A point in a strained material is subjected to two mutual perpendicular stresses of 200 megapascal and 100 megapascal. Determine the intensity of normal, shear and resultant stresses on a plane inclined to 30 degrees with the axis of major tensile strength. So the tensile stress along the x-axis is equal to, is given 150 megapascal, that is sigma x is equal to 150, and tensile stress along the y-axis is equal to 100, sigma y is equal to here given 100 megapascal, and the angle made by the plane with the axis of tensile stress, that is the major axis, it is equal to theta. According to the problem, it is equal to 30 degrees. This is the given data. So, according to the previous derivations, the normal stresses across the section AB is equal to, generally it is represented as sigma n. It is equal to 1 by 2 into sigma x plus sigma y by y minus 1 by 2 into sigma x minus sigma y into cos 2 theta now. This is the relation, it is there now. So, substitute the values of 1 by 2. Sigma x is equal to 200 plus 100. Here 1 by 2, 200 minus 100 into cos into 2 into 30. From this relations 150 by 2, 200 plus 100 is equal to 300 by 2 is equal to 150. Here 200 minus 100 is equal to 100 by 2 is equal to 50. Cos 230 is equal to cos 60. Cos 60 is equal to 0.5. From this relations 150 minus 25 is equal to 125 megapascal. Okay, this is our answer. It is known as the normal stress now. Similarly, the shear stress is equal to tau is equal to 1 by 2 into sigma x minus sigma y sin 2 theta, which is equal to 1 by 2 into sigma x is equal to 200 minus sigma y is equal to 100 into sin 2 theta, sin into 2 into theta is equal to 30 degrees. From this relationship, we got 200 minus 100 is equal to 100 by 2 is equal to 50, that is 50. 2 into 30 is equal to 60, that is sin 60 degrees now. So, 50 into sin 60 is equal to 0.866. From this relation, we got 43.3 megapascal. The resultant stress on inclined plane is equal to sigma r is equal to under root of sigma n whole square plus 2 whole square now. From this relationship, we got it is equal to 125 whole square plus 43.2 whole square. It is equal to 132.3 megapascal. This is our answer now. Here, third problem, subjected to direct stresses into mutual perpendicular directions now. It is similar to the previous problem only. The stresses at a point of mission component are 150 megapascal and 100 megapascal, both tensile, that are treated as positive now. Find the intensities of normal, shear, resultant stresses on a plane inclined at 55 degrees with the axis of the major tensile stress. Also, find the magnitude of maximum shear stress in the component. So, the given data problems, the problem is, first of all, I am representing the forces which are acting on a body. Here, it is having uniform cross section assume. This is known as sigma x now, that is the stresses acting along the x directions, and these are the stresses acting along the y directions now. Both are in tensile. According to our problem, the stresses along the x direction is equal to 150 megapascal. It is equal to 150 megapascal. And along the y direction is equal to 50 megapascal. The plane is inclined to 55 degrees now, is given. This is called a flame now. Here, it is equal to 55 degrees. This is the given data. So, the normal stresses on the inclined plane is given by the relations now. Sigma n is equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 into cos 2 theta now. From this relations, 150 plus 50 by 2 minus 150 minus 50 by 2 into cos 2 theta, cos into 2 into 55. From this relations, we got 100, that is 150 plus 50 is equal to 200 by 2 is equal to 100. 150 minus 50 is equal to 100 by 2 is equal to 50. Cos 110 degrees, it is equal to 100 minus 50 into cos 110 is equal to a negative of 0.342 megapascal. From this relationship, it is equal to 100 plus 17.1, it is equal to 117.1 megapascal. The shear stresses on inclined plane is equal to tau is equal to sigma x minus sigma by 2 into sin 2 theta. From this relation, 150 minus 50 divided by 2 sin 2 theta sin into 2 into 55 degrees megapascal. From this relation, we got to here 50 sin 110 degrees. From this relation, which is equal to 50 into sin 110 degrees equal to 0.9397 and doing multiplications we got it is equal to 47 megapascal now. The resultant stress on the inclined plane is equal to here sigma r is equal to sigma n whole square plus 2 whole square, which is equal to 117.1 whole square plus 47.0 whole square. So it is equal to 126.2 megapascal now. The maximum shear stress in the component it is obtained when sin 2 theta is equal to 1 is required. Sin 2 theta is equal to 1 means the angle it may be 45 degrees or 135 degrees, but the maximum value is equal to 2x is equal to sigma x minus sigma y by 2 now. So here 2 maximum is equal to sigma x minus sigma y by 2. It may be plus or minus, it depends upon the angle. Theta is equal to 45 degrees, the value is nothing but positive. If it is a 135 degrees, nothing but just negative in opposite direction, the meaning is. So that's why we are taking this value is plus or minus sigma x minus sigma by 2. 150 minus 150 divided by 2 is equal to 100 by 2, it is equal to 50 megapascal plus or minus now. It depends upon the values of theta. Theta is equal to maybe 45 or 135 degrees now. A plane element in a body is subjected to a tensile stress of 100 megapascal accompanied by a shear stress of 25 megapascal. Find the normal and the shear stress on a plane inclined at an angle of 20 degrees with the tensile stress. And the second bit is the maximum shear stress on the plane now. In the problem number 4 now, the given data is a plane of element of a body subjected to tensile stress of 100 megapascal accompanied by shear stress now. That means here now, here this is known as our object. It is a direct stress sigma x because we are taking x direction now. It is accompanied by shear now. Shear nothing but here which tends to rotate the body in a clockwise directions now. Here it is assume just like this now. So it tends to rotate in clockwise positive, hence it is nothing but here in downward directions now. Here downward direction, here downward directions, here it is upward directions now. Now just we are taking the relations now. What is the given data in the problem? The tensile stress along the x-axis is equal to 100 megapascal. It is equal to sigma x is equal to 100 megapascal and shear stress is equal to 25 megapascal. This value is equal to 2xy we are calling. It is equal to 25 megapascal now. The angle made by the oblique plane is given by here angle nothing but here it is making. Generally it is 90 degrees. This angle is equal to theta. Theta is equal to how much? 20 degrees is given now. So the required find the normal and shear stresses on a plane inclined at an angle of 20 degrees with the tensile stress. So according to the problem, sigma n is equal to, that is the normal stress is equal to sigma x by 2 minus sigma x by 2 into cos 2 theta, which is minus 2xy sin 2 theta now. So this is equal to 100 by 2 minus of 100 by 2 into cos 2 theta is equal to 2 into 20 degrees minus 2xy is equal to 25 into sin 2 into 20 megapascal, which is equal to here 100 by 2 is equal to 50, 100 by 2 is equal to 50, cos 2 into 20 is equal to 20 equal to 40 minus of 25, 2 into 20 40 sin now. So from this relationship 50 into cos 40 is equal to 0.766 minus 25 into sin 40 is equal to 0.6428 megapascal now. From this relationship we got 50 minus 38.3 is equal to minus 16.07. Finally we got this value is equal to minus of 4.37 megapascal. That is what are the directions we assumed. The normal stress is nothing but acting in opposite directions. The meaning is the shear stress on the plane is equal to sigma x by 2 sin 2 theta minus of 2xy cos 2 theta. Here sigma x is equal to 100 by 2, sigma x by 2 is equal to sin 2 theta is equal to sin into 2 into 20 degrees minus of 25 into cos 2 theta cos 2 theta is equal to 2 into 20 degrees. From this relation 50 into sin 40 minus of 25 into cos 40. From this relation 50 sin 40 is equal to 0.6428 minus 25 cos 40 is equal to 0.766. From this relation we got 32.14 minus 19.15. It is equal to 12.99 megapascal now. The shear stress in the plane is equal to, it is under root of sigma x by 2 whole square plus 2x whole square. It is equal to 100 by 2 whole square plus 25 whole square. Finally, we got this value is equal to 55.9 megapascal. Stresses on oblique section of a body subjected to a simple shear stress. An element is in a strained body subjected to a tensile stress of 150 megapascal and a shear stress of 50 megapascal, tending to rotate the element in anti-clockwise directions. Anti-clockwise direction means here the shear stress is a negative values now. Find the magnitude of the normal and shear stress on a section inclined to 40 degrees with the tensile stress, and the magnitude and direction of maximum shear stress that can exist an element. Here, when they are representing on a object now, this is our element, it is there of uniform cross section now. It is subjected to a tensile of 150 Pascal. This is nothing but assume x direction now, sigma x and sigma x. It is equal to 150 megapascal and shear stress is there now. It tends to rotate the body in anti-clockwise directions now. That is here it is acting in this directions now. Because this effect it is rotating in anti-clockwise directions. Hence this shear stress is treated as a negative according to the analytical method now. So here now the tensile stress, the given data in the problem is the tensile stress along the horizontal direction is equal to sigma x is equal to, already we indicated, it is equal to 150 megapascal. Shear stress is equal to 50 megapascal, but it is rotating, tends to rotate the body in anti-clockwise directions, hence it is a negative. And the angle made by these sections with the tensile stress is equal to theta is equal to 40 degrees already given. So that is nothing but, if I draw the lines, this is known as oblique plane, it is equal to 40 degrees now. So the normal stress on inclined section is equal to sigma n is equal to sigma x by 2 minus of sigma x by 2 into cos 2 theta minus 2xy sin 2 theta. So substituting this value, sigma x by 2 is equal to 150 by 2, sigma x by 2 is equal to 150 by 2 into cos 2 into 40 degrees minus of minus 50 into sin 2 into 40 is given, which is equal to 75 minus 75 into 0.1736 plus 50 into 0.9848 megapascal. From this relation we got 75 minus 13.02 plus 49.24 is equal to 111.222 megapascal now. The shear stress on inclined plane is equal to tau is equal to sigma x by 2 into sin 2 theta minus of 2xy cos 2 theta now. It is equal to sigma x by 2 is equal to 150 by 2 into sin 2 into 40 is given minus of minus 50 into cos 2 into 40, which is equal to 150 by 2 is equal to 75, sin 80 is equal to 0.9848, minus into minus a plus we get now 50 into sin here cos 80 is equal to 0.1736. From this relation we got 73.86 plus 8.68. It is equal to 82.54 megapascal now. The maximum shear stress and its direction that can exist on the element we have to determine. Here 2 maximum is equal to, maximum shear stress is equal to plus or minus under root of sigma x by 2 whole square plus 2xy. It is equal to 150 by 2 plus minus of 50 whole square. It is equal to 90.14 megapascal. The maximum is it may be occur at theta is equal to 45 or 135. Hence we have taken it to the plus or minus values. That nothing but 135, nothing but treated in opposite directions now. Now the direction of here given theta x is equal to angle with the maximum shear stress that makes with the x axis now. According to the relation to tan 2 theta x is equal to sigma x divided by 2 xy, it is equal to 150 divided by 2 into 50 into 1.5. 2 theta x is equal to 56.3 degrees now. From this relation, theta x is equal to 28.15 degrees, or it is also equal to 118.15 degrees now. Here, these problems up to just 5 problems which are related to the analytical method. Here, we are solving these problems by using Morse circle now. The Morse circle is also, when compared to analytical method, it is a method to determine the normal shear as well as the resultant of normal shear forces easily by constructing a circle. It is known as Morse circle now. Here, the problem is a wooden bar is subjected to a tensile stress of 5 megapascal. What will be the values of normal shear stresses across the section, which makes an angle of 25 degrees with the direction of the tensile stress now. Here the given data is the tensile stress is equal to 5 megapascal. Angle made by the section with the direction of the tensile stress is equal to 25 is given now. Okay, these are represented in a figure now like this now. This is an objective plane figure having uniform cross section. It is subjected to a direct stress sigma, which is equal to 5 megapascal now. Here theta AB is representing the oblique plane now, making an angle of theta with the clockwise directions with respect to the x-axis now. So according to the normal method, the analytical method, normal stresses across the section AB is equal to, we are having sigma n is equal to sigma by 2 minus half sigma cos theta by 2, which is equal to sigma by 2 is equal to, here 55 is given, 2.5 minus 2.5 cos 50. From this relation 2.5 into minus of 2.5 into 0.26428, which is equal to 2.5 minus 1.607, or it is equal to 0.89 megapascal. The shear stress across the section is equal to 2 is equal to sigma by 2 into sin 2 theta, which is equal to sigma by 2 is equal to 2.5 sin 50, which is equal to 2.5 into 0.766, which is equal to 1.915 megapascal. This is nothing but relations we use for analytical method for determination of shear stresses as well as the normal stresses. Here, according to the Morse circle now, draw a circle of straight lines, so that is the horizontal lines, and of which is represented as the x-axis as shown in figure. At a convenient point, just O, just to put it now, represent a J on it, such that OJ is representing the 5 megapascal, that is the tensile stress now, according to the suitable scale now. The suitable scale is nothing but I am taking now, that is 1 megapascal here representing the 10 mm or 1 centimeter, so I am taking now. Now, after that, take C as center, that is here, first draw the x and x taken horizontal lines, take one reference point O on it, just represent to OJ. OJ is representing the length of the tensile stress acting on the plane according to some suitable scale. Now draw a line CP, which is making an angle of 2 theta with the OJ, but measured in clockwise directions, such that it meets the circumference of the circle at a point P now. Now from P, draw perpendicular to meet the OJ at a point Q, and also join with the point O now. Now according to the Morse circle now, the OQ is representing the normal stress, and PQ is representing the shear stress, and OP is representing the resultant of shear as well as the normal stress. So according to the trigonometric relations now, here the normal stress is equal to, according to the problems, OQ, it is equal to sigma by 2 minus half sigma cos 2 theta by 2 now. That means nothing but the same values we are getting now. Similarly, the shear stress is equal to a PQ. PQ is equal to, we can take it as OC into sin 2 theta. OC is equal to sigma by 2. That is sigma by 2 into sin 2 theta. We got it now. And substitute the values, we got 1.915 megapascal. Only thing is nothing but if we measure this PQ according to the suitable scale, we will get the values of shear stress, and OQ is representing the normal stress. The values is equal to 0.81 as well as 1.915 respectively now. A point in a strain materials is subjected to two mutual perpendicular tensile stresses, 200 megapascal and 100 megapascal. Determine the intensities of normal, shear and resultant stresses on a plane inclined at 30 degrees with the axis of minor and the major tensile stress now. So the given data in the problem is the tensile stress along the x-axis is equal to, that means if I draw the figure like this, here it is given sigma x, it is equal to 200, and here if I take this is nothing but equal to 100 and 100. So here now along the x-axis is equal to 150, along the y-axis is equal to 150 now. The angle made by the plane with the axis is equal to theta is equal to 30 degrees now. Got it now. The normal stresses across the section AB is equal to, according to the analytical method, 1 by 2 into sigma x plus sigma y minus 1 by 2 into sigma x by sigma y into cos 2 theta now, which is equal to here 200 plus 100 by 2 plus 200 minus 100 by 2 into cos 2 into theta is equal to 30. From this relation, so 200 plus 100 is equal to 300 by 2 is equal to 150 minus of 200 minus 100 is equal to 50 into 0.5 cos 60, which is equal to 125 megapascal. Similarly, shear stress is equal to, according to this one now, tau is equal to 1 by 2 into sigma x minus sigma y into sin 2 theta. It is equal to 1 by 2 into sigma x is equal to 200 minus 100 sin 2 theta is equal to 2 into 30 degrees, which is equal to 50 into sin 60 or 50 into 0.866, which is equal to 43.3 megapascal now. The resultant is equal to under root of sigma n whole square plus 2 whole square, which is equal to 125 whole square plus 43.3 whole square equal to 132.3 megapascal. These are nothing but values obtained according to the analytical method. So we can solve the same problems by using a graphical method, or it is also known as the Morse circle now. So according to the Morse circle now, first of all draw the line now. Here draw the lines. Generally it is representing xx now. The xx. Select a suitable point on it, that is the O, and represent the points on it to O, J as well as the OK toward the right side of the point O, because the tensile stresses both are intensile in nature. Hence, OK is representing the sigma y, OJ is representing the sigma x now. Here Kj is representing the sigma x minus sigma y is equal to here Kj now. Just Kj is nothing but take as a diameter now. With a C as center, draw a circle now. Draw a circle. Here OK and OJ, that is representation of tensile stresses according to some suitable scale is required now. Now suitable scale means I am taking sigma x is equal to 200 megapascal is given. Here I am taking this is equal to, here now 100 mm, then nothing but 1 megapascal is representing the here 0.5 mm now. Similarly, sigma y is equal to 100 megapascal is given, which is equal to 50 mm I am taking now. So just to represent the values now. Here Kj is representing the difference of these two values now, that is sigma x minus sigma y. Take C as center and draw the circle now. From C, draw a line which is making an angle of 2 theta to meet the circumference of the circle at a point P now. Now from P, draw a line perpendicular to the OJ to meet the diameter at Q and join O with the P now. So according to this Morse circle now, the OQ is representing the normal stress, PQ is representing the shear stress, and OP is representing the resultant of shear stress as well as the normal stress according to the scale now. So according to the problems now, the values are given now. Shear is equal to, in previous case we have taken 125 megapascal now. This is equal to OQ is equal to 125 megapascal MPa, and shear is equal to this OPQ. PQ is equal to, we got 43.5, and this is nothing but representing the OP values now. So these values we can determine easily by measuring the length of the lines and converting according to the scales what we selected to give the values of stresses in terms of megapascal. Okay, this information I collected from the textbooks I shown in figure table now. The textbooks, reference books, web references as well as the e-textbooks for solving the problems as well as for collecting the information. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.